So, hello, everyone. Good morning, good afternoon, or good evening, depending on where you are. As General Secretary of the SCOR Foundation, I would like to excuse Philippe Trainard, who is busy with a meeting with the SCOR group managers. I am there to pleased to open this webinar on geolearning and to introduce today our speaker, Denis Allard, who is the research director of INRAE, specializing in geostatistics and spatial statistics applied to environment and climate sciences. His work focuses on modeling spatial-temporal data, analyzing extreme climate events, and developing machine learning methods. He leads the Geolearning Chair funded by SCOR Foundation, ANDRA, CCR, and BNP-Paribas, which aims to apply data science to climate and ecological challenges. Our today webinar will share with us the first results of the research done by this chair. It will more precisely present the challenges and some of the advances that have been made in the chair geolearning for the modeling and the analysis of extreme events and the high impact of compound events. Denis Allard will show the recent modeling strategies allow to quantify the frequency and the amplitude of those events. He will illustrate this work on several cases studies: heat waves and fire danger in Provence in France, simultaneous flooding on 2 river basins, teleconnections at the European scale. The chair is filling a vacuum underlined by the IPCC. Even if we know a lot on global warming, we don't precisely know how this will materialize at different natural catastrophe levels. It is exactly what the chair will make clear, a key forward for insurers and reinsurers. Dear Denis, thank you so much for having accepted to lead this seminar. Please, you have the floor for 45 to 60 minutes. Thereafter, we will open the Q&A session that will last at least until 4 p.m. Paris time. Therefore, please don't open the discussion during the presentation, except if you have a question of technical understanding. Reserve your in-depth questions for the Q&A session. Thank you. And Denis, you have the floor.
Thank you very much, Zeying. Hello, everyone, and thanks to the SCOR Foundation for Science for this very kind invitation. The webinar today will be about some of the work that we do in the Geolearning Chair, which, as Zeying said, is funded by SCOR Foundation. I will take this opportunity to talk about extreme events and compound events and show how we can analyze and quantify those. But before starting this webinar, I would like to acknowledge my co-authors, Lionel Benoit, Grégoire Jacquemin, Antoine Eranval, Rita Matouk, and Saïd Obakrim. Saïd Obakrim is today with the University of Lausanne. And please take note that Grégoire, Antoine, and Rita, they are fully funded by the Geolearning Chair. Yeah, so it is well known that we face an increasing number of so-called natural disasters. And recent examples include the storm Boris in September in Central Europe, in September 2024 in Central Europe. That's the top left image. Or the devastating floods in October 2024, same year, in Valencia, and that's the bottom right image. Along these events, which are really extremes, some climate events can have huge impact, even though the recorded values are not so extreme. It is, for example, the case in 2016 in France, which experienced which experienced a succession of heavy rainfall in spring and summer, leading to at least 25% wheat yield loss over a region called the breadbasket, which is the major wheat producing region in France. And actually the same happened in 2024. These losses were due to a succession of adverse conditions at each stage of the wheat season, from sowing to growing and harvesting, but there were not so many extreme values recorded during those years. And for this kind of events, which can have a very important economic impact, the extreme event theory is not always necessary or useful, and we need approaches that go beyond the classical extreme value theory. So in this webinar, I will illustrate how we can model and analyze extreme events and high impact compound events. And it will be illustrated with examples taken from research projects that are part of the Geolearning Chair. So at this point of my introduction, I think it is maybe useful to take a few minutes to explain what the Geolearning Chair is about. First, it is important to emphasize that the word geolearning is a word that we made up. For us, it covers geostatistics, theory for extreme events, and machine learning in an integrated way. And the field of application here is the climate transition, understood in a broad sense. As Zeying said, it is funded by 4 companies: ANDRA, which is the French National Agency for Nuclear Waste Management; BNP-Paribas, which is known by everyone. It's one of the largest global banks in the world. CCR is the national state-owned reinsurance French company. And of course, the SCOR Foundation for Science. The Geolearning Chair gathers 2 teams with excellent research records. On the one side, there is the geostatistics team of the Geoscience Center at the Paris School of Mines. And on the other side, there is the BioSP team at INRAE, which is the French National Institute for Research in Agriculture, Food and Environment. The Geolearning Chair is at the crossroads of 2 major transitions: the digital transition and the ecological transition. On the one hand, we are now faced with an overwhelming amount of data from satellites, sensors, Internet of Things, and other sources. We have easy access to high-performance computing and methods to analyze data from machine learning and artificial intelligence revolution. And on the other hand, there is the context of global warming and climate change, with all the dramatic consequences that we can observe on a daily basis, including increased storms, hurricanes, and wildfires. A less discussed issue, nonetheless very important, is the increasing scarcity of essential resources such as water, soil, forests, and biodiversity. In this context, our aim is to do research to develop efficient tools for using geostatistics, extreme event theory, and machine learning for the analysis of climate and environmental data. Our research is based on case studies with a commitment to genericity for widespread distribution and use. The Geolearning Chair is built around three main lines of research. The first line is about improving our methods and algorithms to handle very large spatial-temporal data sets. And I will illustrate this with the presentation of a new stochastic weather generator. Our second line of research is about hybridizing machine learning techniques and geostatistical approaches. I will not illustrate this second axis today. And our third line of research is about developing theory and methods for extreme and compound events, and I will spend most of my talk about it. Our production includes new methods developed by PhD students and postdoctoral projects. At present, there are 3 PhD students and 3 postdoc students fully funded by the Geolearning Chair. And this year, there will be 2 new PhD projects. Our production also includes developing tools, that is, libraries for our new developments for which we have hired developers. Finally, our production includes training and transfer to companies. And for instance, today's webinar is an illustration of this commitment. Now, before going to the core of my presentation, I think it's useful to give a brief reminder on extreme value theory. Consider we have a sample of n values that could be precipitation or temperature at a given location, for example. And our aim is to do to have a model for the highest values that are the most extreme values among that sample. And we need the model to make extrapolation. For doing so, we set U, which is a large threshold, so that we consider only values that are above that high threshold. They are above U. And we look at the excess above U, so that we look at xi minus U, given that xi is larger than U. And we compute and we define and compute the distribution function of that excess, okay? And we denote this fu of x. Then classical extreme value theory state that as u tends to infinity, this function fu of x tends to a so-called general Pareto distribution that is fully characterized by 2 parameters, sigma for scale and xi for shape. And this GPD distribution takes only one of the 3 forms, which is Fréchet, Gumbel, or Weibull, depending on the sign of the shape parameter xi. So in this setting here, the procedure is now well known and well established. We first estimate the 2 parameters xi and sigma. Once we have these parameters, we know the GPD, therefore we know the fu of x, and we can compute fu of x for any return value. And from that, we can have a return period, and possibly we can quantify the uncertainty. This is well known, well established, and extreme value is very fine in some cases. That is when we have a single variable at a single site for a single phenomenon. But in many cases, we have extreme events that have a spatial extension. Think about heat waves or heavy precipitation. They are not just local, they have a spatial extension. And we can say the same for temporal persistence, like heat waves. They last for several days. And actually, most of the events, they do have both a spatial extension and some temporal persistence. And therefore, we need an extension of the theory to handle extreme events in a spatial temporal context. And then several variables can be involved. There are many examples of that. For example, we could consider drought and heat waves or humid heat waves in tropical regions, or windstorms and submersions, and so on and so forth. There can also be long-distance connections, and I will illustrate that later on. And as I said before, some events can have a very large impact, but they are not extreme per se. So there is a need to go from the extreme value theory, which is well established, to models for extreme events and models to compound events, for compound events. And in the Geolearning Chair, we work on new tools to model, analyze, and quantify these events. So the outline of the talk is now will be the following. I will illustrate, I will present some work on compound events. And from there, I will go to connected extreme events at a more continental scale. And I will finish with stochastic weather generators. So about compound events, this is the topic of the PhD project of Grégoire Jacquemin. Compound events have been defined recently as a combination of multiple drivers and/or hazards that contribute to societal or environmental risk. And in this paper, which is now a reference paper, there is a list or a typology of compound events. For example, there are preconditioned compound events where, for example, heavy rainfall could arrive on soil that are already saturated, and therefore the soil cannot cope with that heavy rainfall, and it leads to larger floods than the same amount of rainfall on a normal soil. There could be temporal succession, temporal compound events with a succession of rainfalls leading, for example, to yield losses, as I illustrated earlier. There could be multivariate compound events and also spatially distributed compound event with, for example, simultaneous floods on large river basins. And this is what I'm going to talk about now. So in this PhD project, we wanted to come up with new ways to analyze spatially compound events. And a motivating case study is the simultaneous flood of two river basins. And this example is comes from the storm Boris, where in fall 2024 we had almost simultaneous floods on the Danube river basin, that's in the region in yellow, and on the Vltava river basin, which is the purple region. Okay, so what I'm going to present now is an analysis of the simultaneous floods on these two basins. And for doing that, we first define a variable on which we can do the analysis. So here we define a cumulative precipitation index, which is defined for each day t. So we have IT, which is defined as a sum of precipitation during the n previous days, including day t. So we sum pt, pt minus 1, and so on and so forth, but we don't sum at them. In order to sum them, we also use a discount rate, which accounts for the fact that some of the rainfall flows or goes in the soil. So we define this index on these two regions, the yellow and the purple one. And we do this sum with a discount rate equal to 0.9 and 17 days, for example. And of course, the precipitation that we consider is the sum over the whole region of the precipitation as given by some reanalysis product. And here we used INRAE 5 data. So now we have these two time series of values, E1 to En for the Vlatvar river basin and for the Danube river basin. And the questions that we might ask ourselves is, are these series independent or not? And if they are not, what is the return period of a simultaneous extreme event? And by simultaneous, what we mean here as an extra complication is that it could be within a week, okay? Because the flood does not exactly happen the very same day. And we first use the Coppola approach, which is well-founded and which is the state-of-the-art in the literature. But the Coppola approach was found to be biased and unstable. So we developed a new methodology, which we will see is more stable and more robust. And this new methodology is called the multivariate generalized Pareto distribution. Let me introduce this very quickly. It's a bit technical, but these are the 2 or 3 more technical slides of my talk. So first, we transform our series of value here. We transform them on an exponential scale. And this is for mathematical reason. I'm not able to detail here because that would lead us far too, it would be a bit long to explain. So now that we have the values on these exponential scale, we cross-plot them on this plot here, okay? And we remove the points that are below some threshold UE. And here the superscript E is there to remind us that we are on an exponential scale. So we remove the points for which, well, we are below the threshold on the 2 series. And we only consider the black dots, and in the black dots, at least one of the series is above the threshold. And then there is a theorem that states that the excesses, okay, so that's the amount of value that is additional to UE, this excess can be decomposed as the sum of an exponential random variable and the process t minus max t that I will now detail a little bit. So we have this decomposition here. In the bivariate case, we only have 2 coordinates. So z is a vector with 2 coordinates, z1, z2. T is a vector of 2 coordinates, t1, t2. So that we can rewrite this expression as z1 equals e plus t1 minus max t1, t2, and same for z2. And you can notice that if I compute the difference z1 minus z2, then the e's cancel out, and the maxes, they also cancel out, so that z1 minus z2 is equal to t1 minus t2, and this I call delta, because it's a difference. Therefore, the decomposition above can be rewritten this way. Z1 is E plus delta if delta is negative, and Z2 is E minus delta if delta is positive. So let's have a look at the cross plot here. So let's consider this point, this red point here, right? So if I go on the diagonal, then I have the value E. That's E. And then delta is the quantity that puts me off the diagonal. And here delta is negative. So Z2 is unchanged and Z1 is decreased by amount delta. So it turns out that once we have this decomposition here, then we are able to compute very precisely, we are able to compute the probability of joint excesses. And this can be used using numerical integration and the empirical CDF of delta. So there is no model here. we don't need to impose a model or estimate parameters, and we can do very precise computations. So this is our new methodology. And of course, once we have a new methodology, we need to validate it. So we did some simulation exercises to validate our approach and to compare it with the previous approach, which was the copular approach. So we simulated data that mimic the real data that we have on this case study. So we simulate exactly the same type of data, but there are synthetic data following a Gaussian copula with temporal correlation. With these, we are able to compute the exceedance probabilities and compare the two approaches. Now, since this is a model we simulate from, we are able to, we know the exact values as well, and we can compare to the exact values. And then we do 150 draws in order to assess uncertainties. So these are the results that we have. On the left plot, we show the excess probabilities, and the horizontal line are the true values. So on the left here we have no temporal correlation, and then here we have temporal correlation. And we can see that our approach, which is the BiGPD approach, leads to much more accurate estimation of the true probability. And especially when there is temporal correlation, which is our case, the copular approach leads to lots of zeros as probabilities. And that's, of course, is not acceptable. And if we look at the relative error instead of the values, we see that our BiGPD approach is again leads to much more accurate estimates, because here again this box plot shows that more than half of the values have exact zeros. So we have this new methodology now. From the simulation study, we know that it's quite accurate and that we can use it. So we go back to the motivating case study, and we apply it on the past. So on the past, we use reanalysis data from ERA 5 on a 30-year period from 1995 to 2024, and also in projection in the future. And for that, we use a selection of 10 global circulation models that are able to project climate in the future. All GCMs were run under the SSP 8.5 scenario. For those who are, well, this is the most pessimistic scenario in terms of greenhouse emission scenarios. So, but unfortunately, it's the most pessimistic, but it's probably the most likely as well. So we use that one, and we applied 5 bias correction methods because, as you may know, we cannot use GCMs directly. We need to post-process them in order to remove some of the bias that is still in these models. So we applied 5 bias correction model. CDFT is sort of quantile method. DOTC is based on optimal transport, and R2D2 are reshuffling, rank reshuffling methods in order to preserve the copulas. Right, so these are our results on these on the Stormberry's example. So we first look at the past. So that's the first panel here, and the true value is in the value computed on the reanalysis data is indicated with the horizontal line. It corresponds to approximately 200 years for the return period. And we compute the return period for the models with no correction in gray and with the 5 bias correction method. And what we can see is that if we apply no correction at all, it is extremely biased. We have return periods that are really, really high, up to 100,000 years and even more. But we stopped the plot at 100,000 years. But once we do the correction, after correction, we are pretty close to the reference data, and we are quite happy with these values. And there is, so the box plot here, there are box plots because we have 10 models. And then since we have 10 models, we have 10 return periods, and we can draw the box plots from the 10 models. And now if we project in the future, we consider 3 periods in the future. So near future, then middle of the century, and then end of the century. And what we can see is that we have more uncertainty as we go further in time. And we can also see some tendency towards decreasing return periods. Okay, and there is a large difference between values on the computed directly on the models and after bias correction. And from the analysis on the past, we know that it is necessary to do the bias correction. So some take-home messages on this compound event work. We have a new approach for quantifying the return period of extreme spatial compound events. It is more robust than the previous Coppola approach. We have seen that when using climate models, bias corrections are needed, and extreme simultaneous floods seem to become more frequent on the 2 studied examples. There are other studied examples that I haven't shown here, but they more or less tells us the same story. That is, the simultaneous floods seem to become more frequent, at least over Western Europe. Now, further work is still needed to scan over the whole Europe and generalize this result to other types of compound events. So, in this example, we've seen two extreme events that were close to each other. Okay, these 2 regions, they were neighbors. And one question that one might ask ourselves is that what happens if we have extreme events that are further apart and as the distance increase? And do we have tools to explore the possible connections between events, either spatially or temporally or across variables? And to answer that kind of questions, we started another project, which is the postdoc project of Antoine Hérenval. And in this project, the challenge is to transform the climate model big data into actionable knowledge on extreme and compound events under climate change. And for doing that, we're going to use methods from point processes. And the objective is to better understand and better model the spatial and temporal co-occurrence of extreme events, but here at continental scale. So again, for the moment, we only use reanalysis data in the past. Of course, we will project that in the future later on. So we selected the 20-year period here, and we downloaded lots of data, lots of variables. And for the moment, we only analyzed temperature and precipitation, and the examples that I'm going to show are about temperature and precipitation. So we first aggregated, we first aggregated our data at a regional scale using the so-called NUTS level, NUTS regions. So these are territorial units defined in Europe, and more or less they correspond to regions. And at least it's the case in Spain, Italy, and France. And it's, well, it more or less corresponds to regions all over Europe. And the idea is that each NUTS has a population, well, they have sort of same amount of population. So for example, well, so France is divided into 25 NUTS, but yeah, but here the smaller countries, they have a single NUT. Right, so this is the spatial level at which we look at the events. And we first constructed our extreme events in the following way. We look at daily values, and then for precipitation, we defined presence absence, and then moderate precipitation. Those are the precipitation that are above the 95th percentile of positive precipitation. And then extreme precipitation are above the 99th percentile of positive precipitation. And for the temperature, we first remove the mean and work on anomalies, and hot events are defined as a temperature that are above the hot events are defined as anomalies that are above the 95th percentile, and cold events are anomalies that are below the 5th percentile. And as I said, we are going to use market point processes to analyze these data. So what is a market point process? It's a collection of discretely observed stochastic events, and each event is characterized by a point, and a point is a coordinate in time and space. So, for example, we could say that the extreme rainfall that occurred in Valencia, that's one point with the date, I think it was 29th of October, and then the coordinate of the appropriate NUT region. And a mark is one or more numerical variables, like the duration or the size or the total amount of precipitation and so on and so forth. Actually, market point processes are statistical methods that are that have been developed since maybe 1960 or even before, and they are very much used for the analysis of earthquakes, lightnings, trees in the forest, galaxies in the universe, you name it, all the phenomena which could be described as a point and a mark. And we can look at those. So, for example, let us have a look at the temporal market point process in Languedoc-Roussillon, 2022. And so the x-axis is time. We have the seasons: winter, spring, summer, autumn. And in purple, what we see is the presence of precipitation. Then we see moderate precipitation in blue. In green, it's severe precipitation. Then we have hot temperature in green, and hot anomalies in green, and orange anomalies in orange, cold anomalies in orange. And you can see that there are circles with different radius. Here the radius is proportional to the duration in days. Okay, so this is a visual representation. It's a data viz of these point processes. Same can be done in another region. So, for example, northern and eastern Finland. But, well, we are able to visualize, maybe to explore, but we are not able to model. So we need mathematics to analyze data and quantify a little bit the data. So the first function that we define to analyze the data is the intensity. The intensity is simply the mean number of events in a time interval. So we define the time interval between 0 and capital T, and we simply count the number of events and divide by the length of T. So that's for intensity. But we would like to compare two series and to see if there is or not some correlation between the two series. And for that, we use the cross-k function. That's its name. And that's the mean number of points of x that are around y. So this is simply the number of points ti of x and sj of y that are less than r days apart of each other. And we count all these pairs of events that are less than r days apart. And we divide then by the intensity of the 2-point processes so that we have something that is standardized and normalized. And it can be shown that this quantity, this function, which is a function of r, quantifies the clustering or dispersion of events around a typical event, so that it's possible to show mathematically that when it's equal to 2r, the two processes are independent. If it's larger than 2r, there is attraction, and if it's less than 2r, there is repulsion. And we have some packages to do that. And here are some results. Let's look at severe precipitation in two neighbor regions, Languedoc-Roussillon and Provence-Alpes-Côte d'Azur. They are both on the Mediterranean shore in France, and they are neighbors. And as I said, if it is independent, then the function should be equal to 2r, up to some border effects. And we are able to compute bounds, which define a 95% confidence region for independence. And these bounds are represented with these red dotted lines. So if our k function is within this envelope, we could say there is independence. But here, as you can see, the k function that we have computed, it's the black line. It's well above this confidence region. And this tells us that there is positive correlation between these two as far as severe precipitation is concerned between these two regions, which is the result we sort of already knew, of course, but it's good to see that the mathematical analysis is able to retrieve that result. So now let us have a look at two other regions, so Languedoc-Roussillon and then northern and eastern Finland. And here the black line is well within the envelope. So this tells us, well, there is independence between for severe precipitation between these two regions. Again, this was to be expected because there is probably 3,000 to 4,000 kilometers between these two regions, and of course they were expected to be independent. So now we looked at the two. Sorry, there is a typo here. Between severe precipitation and temperature anomalies within the Languedoc-Roussillon region. And so temperature anomalies could be cold or hot. And we can see that there is some clustering or attraction between severe precipitation and cold anomalies, and there is independence between severe precipitation and hot anomalies. And this, I think, was not known and is a new result. So we were quite happy to find a result like this. But we still need to dig a little bit into that in order to better understand what's really going on there. And as a last example, we computed in Finland, the cross-K function between hot and cold anomalies. And here you can see that the black function is well below the envelope. That means there is anti-correlation or negative dependence or repulsion between hot and cold anomalies. Here again, that's kind of normal. There cannot be a hot and a cold anomaly at the same time or a few days apart. And actually, independent, the repulsion lasts for almost a month, and independence is reached after 4 weeks in terms of hot and cold anomalies. So here we have a new tool for analyzing compound extreme events. And this is the very beginning of the project. We still need to do some more systematic exploration, find out whether there are typical correlation ranges, maybe some teleconnections, and so on. And in the future, we would like to go to the analysis of convective events like hail and tornadoes using the variable called CAPE. And then project everything into the future using climate models. Okay, but as I said during my introduction, we also have some events that involve the entire sequence of weather conditions. And for that, we need another type of model that is able to model completely the weather sequence. And for that, we use stochastic weather generators. And that's the last part of my talk. Stochastic weather generators are tools, mathematical and computer science tools, that generate random series of meteorological variables, such as precipitation, temperature, and so on and so forth. And they must have statistics that are similar to those of recorded data. So in terms of marginal distribution in the mean, variance, quantiles, and so on, but also in the dependencies between variables, the temporal dependencies, and the spatial dependence. And once we have models for that, we estimate the parameters on recorded series. So the SWGs are calibrated on recorded series. And once we have the model with the parameters, we can perform simulations, and that's very, very computationally efficient. So we are able to simulate long series or large number of realizations, and therefore it's a tool that is complementary to the climate models. They are used in impact studies because the outputs of SWGs are used as alternative plausible weather time series in process-based models. So we were able to play scenarios and to assess uncertainties in complex nonlinear systems, and not only for extreme events, as I said before. So at INRAE, we use it to explore plant and ecosystem models as a function of climate variability, but they are also used in industry for energy demand models or hydrological models and in insurance models. So we selected the domain of interest. Since I am based in Avignon, in the Provence region, we selected the Provence region, not only because I live there, but also because it's an interesting region because it's highly non-stationary. So the idea was, if we are able to do something on the Provence region, then presumably we will be able to do it everywhere. So this region is very non-stationary. We have the coast in the south, and we have the Alps in the north and in the east. So it's a quite challenging region. We considered 6 daily variables: precipitation, humidity, radiation, wind, mean and max temperature. And as reference, we use the Safran reanalysis data from 2012 to 2021. The Safran reanalysis data are defined on an 8 by 8 kilometer grid. So that gives us almost 500 pixels. We have 6 variables, 10 years of data. Therefore, that's 11 million data. So we had to define a stochastic model. And the stochastic model that we built is grounded on 2 main assumptions. First assumption is that there are a finite number of weather types that over the region. And here we found that 6 weather types were enough to describe for this region. A weather type is, for example, it's sunny and dry everywhere. That's type 1. And type 2 would be it's cloudy, but not too much raining. And this is approximately true everywhere. And then we would have type 6 is it's raining everywhere on the region. So these weather types, they make sense at a regional scale. Maybe it would not be a good tool at a larger scale, such as a national scale or even the continental scale. So in each weather type K, and for each variable I, there are 6 of those, remember, and each location S, there are 500 pixels. The weather variables are modeled as a transformed latent Gaussian random field. And thanks to a transform function here denoted psi chi is. So there are many of those functions because there is one function for each combination of k, I, and s. The weather states are then modeled as first-order Markov chain with the transition matrix pi, but the transition matrix is allowed to vary in time during the year from day 1 to day 365. For the function psi, we did not use a parametric model, but instead we use the empirical transformation with tail adjustment for very low and very high values, as described in this paper here. And for the multivariate spatio-temporal model, we used Gaussian random fields, and Gaussian random fields are fully characterized by their expectation, which is set to 0 here, and by their covariance kernel. And here we used as a covariance kernel a new family that was that I defined a few years back, but I will not show it here because it's extremely technical. So once we have estimated all the parameters, we are now able to do the simulation, and it goes as follows. We first simulate the weather states according to the Markov chain. Then in each weather state, we sample the multivariate random field. That's a cube of a value. It's a cube because we have a temporal dimension, a spatial dimension, and then the variable, that's the third dimension. And this cube of value is then transformed into weather variables using the whole set of psi functions. And then at the end, we have the weather variables. So we wanted to sort of validate the stochastic weather generator. So the first validation was to look at the PDFs that we simulated. So here are a bunch of PDFs for the 5 variables for all the continuous variables. So precipitation is not shown here. And the 4 seasons, winter, spring, summer, and autumn. The red curve is the PDF computed on the recorded series. And there are 20 gray curves because we performed 20 times 10 years of simulation. So we have a 10-year simulation is so that that's similar to the 10 years of recorded values. And we have 20 repetition of that. So we have 20 simulated densities. And what we can see here is that the recorded PDF is well within the envelope of the 20 simulated PDFs. That was sort of to be expected because we used a empirical transformation that works really well, and we are even to reproduce even bimodal PDFs, which probably a parametric model would not have worked for that. Okay. So now we did a lot of validation, and I'm only going to show you two other validations. The first one is about heat waves. Heat waves are defined by the French regulation as 3 successive days with the minimum temperature above some threshold and maximum temperature above another threshold. And the thresholds, they depend on the exact location we are looking at. And we used the values that defined the heat waves in Marseille, and because Marseille is the largest city in the region. So these two values correspond to the definition of heat waves in Marseille. On the left panel, we have the observed frequency of heat waves, and on the right panel, we have the simulated frequency of heat waves on a 10-year simulation. And we can see a slight underestimation of the frequencies of of the heat waves. But it should be remembered that in this SWG at the moment, there is no model, specific model for extreme values. And there is therefore here certainly need for improvement of the modeling of extreme values and their temporal persistence. Our second validation is on the fire weather index. This is an index which was developed and is still maintained by the Canadian Forest Service. Here is a schematic view of how it is computed. It consists of 6 components that account for the effects of fuel moisture and weather conditions on fire behavior. And it is updated daily using the values in these 6 modules of the day before, and then it's updated with the 4 weather variables: temperature, rain, wind, and humidity of the current day. And that defines the new FWI value. And actually, it is used in France at the department level as an alert system to say, well, this is maybe a red day, so access to forest is forbidden, and that kind of things. Okay, so it's very. I think it is a relevant validation to use this fire weather index because it is used on a daily basis in France during the summer. So let's have a look at the summer average. So here we look at the mean. The first column is observed value, and then we have simulated values, and then we have the bias. That's the difference between simulation and observation. Considering the mean, the bias is really low, but there is some bias in the extreme values of FWI, because this is the 95th percentile, this is the 99th percentile, and we can see that there is some bias. However, the bias is in absolute value, it's maybe between -5 and +5. And here the values are around 40, 50, or even 60. And actually, the alert system starts in France with a value of 25. So there is a bias, but it's not a huge bias. If we look at the densities, so we plotted the densities at 4 locations, Marseille here, and then 3 well-known forest massifs in Provence, Les Maures, Mercantour, and Sainte-Victoire. And again, the red curve is the PDF on the at that location on the recorded values during the summer. And the gray lines are the PDFs computed on 20 repetition of 10-year simulation. And again, we see that the red curve is well within the envelope of the gray curves. So we are able to reproduce the PDF of the fire weather index at those 4 locations. And then we can have a look at the temporal dynamics of it. Again, these 3 in these 3 forests here. So we have that's during the summer from day 142 to day 272. Actually, the summer is between these 2 black lines here and there. And the mean is indicated in blue, the max is indicated in red, and the minimum is indicated in green. The observed values are the continuous lines, and the simulated values are the dotted lines. And we can see that there is a pretty good reproduction of the dynamics for the mean and the maximum at these 3 locations. Okay, so here on this part, I think one conclusion is that it is possible to design a spatial multivariate stochastic weather generator that has quite good statistical performances. It is only one among many possible statistical models, of course. The code is available on GitHub at this link here. And the paper is in press in a journal called SERA. It's Stochastic Environmental Research and Risk Assessment. It's in press. As I said before, well, there is future work that we consider here. First of all, we would like to include non-stationary covariance because at this time we use stationary covariance. And then we would like to improve the temporal persistence, and in particular for long period of droughts. And for that, I would like to mention that there is a PhD student, Antoine Doisé, maybe he's listening, I don't know, that is funded by the Chair Geolearning to precisely work on new generation of SWGs that are able to account for long period of droughts and extreme values for precipitation at the same time in the same model. Okay, I think that's it. Thank you very much for your attention, and please do not hesitate to visit our website at this address. Thank you very much. I think I'm ready to take questions if there are some.
Yeah, so we thank you very much, Denis, for this high interesting and insightful presentation, and to share with us, the results of how do we say the further results made by the share, and illustrated by some concrete cases. And now we open the Q&A session. So please feel free to raise your question or your remark. Or you can also send your questions, on the chat. No one question from the participants? The Henri.
No, I don't have a question because I think I'm supposedly should know all the topic here. I missed a bit the beginning, but did you introduce a bit the concept of this the partnership we have between SCOR and
Yes, I did.
Okay, very good. So I guess you can understand for SCOR that, I mean, one of the issue is we know there is some climate change, or the climate will change in the future, and but what we don't know how the extreme will change with the climate change, and that's why we need to seek research on it. And I mean, analyzing extreme on stationary climate is already sometimes complex. So on non-stationary with climate change is even further complex. And you can see you need quite a lot of math and science to do this kind of thing. So that's why we have this partnership. I don't know if there is any question or what we're expecting to get from this research or this kind of things. No question.
Okay, maybe how do I say police share Henri Bovy and Marie-Laure Fander. They work closely with Denis and his research team. So it's really very how do I say very reactive share. And what I would like to say, maybe if you have further questions, maybe you can send me Henri Bovy. Some question we can after transfer to Denis. And also just to say this webinar is recorded. So as if Denis agrees, we will put it on the SCOR Foundation's seed web with along with the presentation. So thank you very much. Thank you again, Denis, for your for this excellent and very insightful presentation. So we learned a lot. Okay.
Yeah, I may have an indirect question because I was chatting when one of the participant Yuye, and I'm sure she will be interested to see whatever we can do some sort of similar analysis we did, example with the compound event, maybe outside of Europe, and because she's working in Southeast Asia. Whatever we could do a similar analysis on maybe a few past events in the region. Will it be possible?
Yeah, it's so.
Please.
Do I need to answer that question? Yeah, I guess.
No.
Yes. Well, in principle, it's possible. Now, how we do that is to be discussed. I mean, yeah. But it requires some time because we need to download the data and then define precisely the event we're looking at, then build some kind of indicator that reflects that event, and then do the computations. Doing the computation, that's pretty fast, but it's everything that's before that, defining the event, having the data, and so on and so forth. That's not obvious. It takes a few days. at the moment.
I see. I mean,
We
yeah,
don't have an
I
automatic
mean,
pipeline.
yeah, I mean, I do appreciate what you have shared. It's very interesting. As Henry mentioned, also have a need from Asia. So I'm based in Hong Kong. So we are looking for solutions also for the APEC region. Yeah. So I mean, I leave it. I mean, me and Henry we're in constant talks. So if we have this in mind to put in the pipeline, that'd be really appreciated.
Thank you very much.
Yeah.
All right. So it was an indirect question, as I mentioned.
Thank you. Yeah.
Okay, so if they don't have any other questions, maybe we will close this webinar. And thanks again to Denis for this very interesting webinar. And thank you to all participants. And see you next time.
Thank you to all.
So, bye-bye.
Thank you for listening.
Thank you.
Thank you.
Thank you. Bye.